Hello and welcome to this lesson on the limit of a function. I'm Mohamed Kadem Kare. You may download the PDF of this lesson on the website I indicate here, and it will also be indicated in the description below the video YouTube. The outline of the lesson will be firstly to define the notion of limit of a function. Then I will present operations on the limits. After that, I will describe the sandwich theorem, the right and left limits, and finally, I come to the asymptotes. Let's begin by defining the notion of limit of a function. So here is an example. I plot the function expressed here in a red color, and you see that when x approaches 2 here, f of x approaches infinity. Also, when x approaches infinity, f of x approaches this value here, which equals 1. We aim to give a precise meaning to this statement of limit of a function at some point or at infinity. Remind that the set of real numbers R is the set comprising numbers such as these ones. A function is a mapping from the set of real numbers to itself, associated to each x an image called f of x. Before giving the formal definition of limit, let's make or give some intuition. The fact that the limit of f of x when x goes to a equals L means that when x is close to a, its image f of x is close to L. X is close to a can be formalized by saying that x is within an interval a minus delta, a plus delta, for some small enough delta. We say in this case that the interval here is a neighborhood of a. So keep in mind this notion of neighborhood of a point. It is an interval containing this point. Note also that the fact that x is within this interval is equivalent to the fact that x minus a is in absolute value smaller than delta. On the other hand, x is close to infinity can be formalized by saying that x is larger than k for some large enough k. We say in this case that the interval k plus infinity is a neighborhood of plus infinity. Also, the fact that x is close to minus infinity may be formalized by saying that x approaches minus infinity, may be formalized by saying that x is smaller than minus k for some positive k large enough. So we say in this case that minus infinity minus k, the interval minus infinity minus k, is a neighborhood of minus infinity. So in this slide, I define the neighborhood of any real number, a, the neighborhood of plus infinity, and the neighborhood of minus infinity. I give now the precise definition of a limit of a function. Let f be a function from the set of real numbers to itself. We say that f of x has a limit L when x approaches a, and we write it like this. the limit when x approaches a of f of x equals L if any neighborhood of L contains all the values of f of x for any x in the neighborhood of a such that x is different from a. So this condition is an important condition which is sometimes omitted by some authors because the limit is not concerned but what it happens at the point A precisely. So all we consider are points approaching A while being different from the point A precisely. So formally this may be written like this. If a is a real number and the limit L is also a real number, it may be written in with the epsilon delta statement, which says that for any epsilon there exists some delta such that if x is the interval a minus delta, a plus delta minus a, this implies that f of x is within the interval L minus epsilon, L plus epsilon. So this is a neighborhood of L, since L is a real number, and this is a neighborhood of A, since A is a real number also. In the case where A is plus infinity and L is a real number, it may be written like this. For any epsilon, there exists some real number, positive real number k, such that when x is within the interval k plus infinity, f of x is within L minus epsilon, L plus epsilon. So you see that in this case, since a is plus infinity, we consider a neighborhood in this form. And since L is a real number, we consider a neighborhood in this form. The other cases where a is minus plus infinity is a minus infinity, or L is plus or minus infinity, you may written equivalent statements like that. Okay, so just adjust the neighborhood to the appropriate point or limit. I give now some examples. The limit of 1 over x when x goes to infinity is 0. The limit of x squared when x goes to infinity is infinity, since when x increases, x squared also increases, and so it goes to infinity. The limit of minus 3x when x goes to infinity is minus infinity. We present now results on operations on the limits. We can do the sum, the product, or the ratio of the limits as long as there is no ambiguity. For example, if you have two functions f and g, such that the limit of f is L at some point and the limit of g is L prime, so we have f goes to L and g goes to L prime, as for example x goes to some a, then the sum f plus g will tend to L plus L prime as long as this sum has a clear sense. Here are some examples. If we consider the limit as x goes to 2 of this product here, we see that this term approaches 2, this term here approaches 5, so the product will approach 10. Also, when x tends to 0, the numerator here approaches 0, the denominator approaches 1, and so the ratio will approach 0. Also, the product here, when x goes to infinity, this term goes to infinity, but this term also goes to plus infinity, so the product will go to plus infinity. But in some cases, unfortunately, we have an indeterminate form. For example, if we have the ratio infinity divided by infinity, or 0 divided by 0, or 0 multiplied by infinity, and also if we have plus infinity plus minus infinity. In these cases, the expression must be transformed to get the right limit. I'll present now some methods to remove indeterminacy. The first method is by factorization. So imagine that we have to calculate the limit when x goes to infinity of this ratio here. You see that the numerator tends to plus infinity, but also the denominator tends to plus infinity. So we have an indeterminate form, and to remove this indeterminacy, we have to factorize by x in the numerator and by x also in the denominator. In this case, we can simplify this x here and we get this ratio, but each term of this ratio goes to 1 now. So the ratio tends to 1 also. 1 divided by 1 equal 1. More generally, when you have the ratio of two polynomials, you have to factorize by the term with the highest degree. In the numerator here, the highest degree is x squared, so I factorize by x squared. The denominator, the highest degree is x to the power 3, so I factorize by this term here. And by this way, we get also this ratio here. So the numerator will go to 1. The denominator will go to plus infinity multiplied by 1, which goes to plus infinity. So the limit here is 1 divided by plus infinity, which gives 0. Here is a second method to remove indeterminacy when calculating the limit. It is based on a remarkable identity saying that a minus b multiplied by a plus b equals a squared minus b squared. If we apply this identity with the square root of x in place of a and square root of y in place of b, we get this second equality. And in the particular case, when y equals 1, we get this equality here, the square root of x minus 1 multiplied with the square root of x plus 1 equals x minus 1. We say that the square root of x plus 1 is the conjugate form of square root of x minus 1. Here is an example. If we try to calculate the limit as x approaches 1 of x minus 1 divided by square root of x minus 1, we see here in the numerator that we get as limit 0, but also in the denominator the limit is 0, so it is an indeterminate form. But if we multiply both sides by square root of x plus 1, which is the conjugate form of this term here, we get that the numerator and the denominator comprise the term x minus 1, and we can simplify by this term. So the remaining term, which is square root of x plus 1, gives the limit, which is 2. We now state a result about the limit of composition of functions. Remind that if we have two functions, f and g, the function associating to each x, g of f of x, is called composition of f by g. We denote g composed of f of x equals g of f of x. So the theorem says that if f has a limit b at some point a, and if g have limit c as x approaches b, which is the same point here, then in this case the composition g by f when x approaches a will give the limit c. Here is an example to be more concrete. When x approaches 1, the limit of this square root is calculated as follows. Firstly, we consider the limit of this term here, which gives 5 as x approaches 1. And then, since the limit of square of x when x approaches 5 is a square of 5, we get that the limit of the composition here equals the square root of 5. So it is a natural application of the composition of two limits, one after another. We now state the sandwich theorem. This theorem, very useful in practice, says that if a function f is between two functions g and h, where g and h have limits as x approaches a, which are the same. Here the limit is L, and here also the limit is L, some real number. Then in this case, the limit of f as x approaches a is also equal to L. The second statement of this theorem says that if f is larger than some function g, where the limit of g is plus infinity, then the limit of f also equals plus infinity. The last statement says that if f is smaller than some function h, which has limit minus infinity, then the limit of f is also minus infinity. Here is an example. If f is between these two functions here, so let's see what happens when x goes to plus infinity. This term here goes to 2. This term also has a limit 2. So the function in between has limit also 2. Note also that the sandwich theorem is known also as the squeeze theorem. Let's do together this exercise as an application of the sandwich theorem. So we aim to calculate the limit as x goes to infinity of sine of x divided by x. And we want to show that this limit equals 0. The idea is to start from this result that the sine of x is between minus 1 and 1. Then for any positive x, we can divide this inequalities by x, and we get this sequence of inequalities. Now, when x goes to infinity, this right-hand side goes to, I will erase a little bit, okay? So this right-hand side will go to 0 as x goes to infinity. The left-hand side also goes to 0. So the function in between also goes to 0. So this is an immediate application of the sandwich theorem. We introduce now the notions of right and left limits. So the context is the following. Let f be a function from the set of real numbers to itself. We say that the function f has limit L when x approaches a to the right, and write this as follows. The limit as x approaches a plus of f of x equals L if any neighborhood of L contains all the values of f of x for any x in the neighborhood of a such that x is larger than a. So let's make a figure here. Assume that the point A is here, and now we are interested on what happens when x approaches a to the right. Okay? So we are interested in the limit of f as x approaches a, we say a plus, to say that x is on the right of a. Okay? So here is the limit when x approaches a to the right. On the other hand, we say that f of x has limit L when x approaches a to the left this time, and we write it x goes to a minus, to say that it is on the left of a, if any neighborhood of L contains all the value of f of x, when x is a neighborhood of a such that x is smaller this time than a. So it is a symmetric figure. Up. Here is a, and now we are interested when x approaches a to the left. And we write it here, the a minus, to see that in the left side of a, and the limit in this case is this one, okay? This limit here. Here are examples. Let's consider the limit of 1 over x when x goes to 0 plus. So let's make a figure here of 1 over x. This is the figure of 1 over x. So when x approaches 0 to the right here, the limit of 1 over x is plus infinity. On the other hand, when x approaches 0 to the left, f of x goes to minus infinity this time. So the right-hand side limit is plus infinity, whereas the left-hand side limit is minus infinity. And since the right and left limits are different, the limit of 1 over x when x goes to 0 does not exist. So for the limit to exist, we have to assure that the right limit and the left limit exist, and the two limits are the same. The last part of this lesson concerns asymptotes. So we begin by defining the horizontal and vertical asymptotes. Let C be the curve of a function f. If the limit of f as x goes to infinity equals L, let's make a figure here. So this is x going to infinity, and assume that the limit of the function f is some value here, L. In this case, we say that the curve of f admits a horizontal asymptote with equation y here equals L. So this is the equation of the asymptote, the horizontal asymptote. On the other hand, if the limit of the function f at some point a here is plus infinity, for example, like this, so this is the limit as x approaches a, is plus infinity. In this case, we say that the curve of f admits a vertical asymptote this time with equation x equals a. Since you see that in this case, we have this line here, the straight line here is an asymptote of the curve of f. This is also the case if the limit when x approaches a to the right equals a. So assume that we have the limit of f when x approaches a to the right is a, is plus infinity, or the limit when x approaches a to the left equals either plus infinity or minus infinity. In all these cases, we say that this line here of equation x equals a is a vertical asymptote of the curve of f. Let's see together an example. Consider the function f given by this expression here. So the limit of f as x goes to plus infinity, here you get plus infinity, and over plus infinity is 0, plus 1, the limit is 1. So since the limit of f equals 1, then the curve of f admits a horizontal asymptote with equation y equals 1. So I make a figure here. The limit is 1, so the function is decreasing up. So we have a limit equals 1. So this line here is a horizontal asymptote. On the other hand, the limit of f as x goes to 2 equals plus infinity. I make a figure up. This is the value 2. The function f goes to plus infinity as x goes to 2. So the curve of f admits a vertical asymptote of equation x equals 2. So here is the curve of this example. So the function is plotted in red here. This is the curve of the function f. And we have the horizontal asymptote of equation y equals 1. It is an asymptote at plus infinity and minus infinity. Here is the same asymptote. And also we have an asymptote at x equal 2, which is a vertical asymptote here, since the limit equals plus infinity. In the last part of this lesson, I will introduce the notion of oblique asymptote. Let C be the curve of a function f from the real set to itself. If the limit of f minus some ax plus b equals 0 as x goes to infinity, then we say that the curve of f admits an oblique asymptote with equation y equals ax plus b. So this is the equation of the oblique asymptote. Okay. Here's an example. Consider the function which is the ratio of two polynomials here. We can decompose it in this way. So here this is 1 over x here, and this is the first part. Okay, so there are two fractions. In the first fraction we factorize by x in the numerator here, and so we can simplify x and we get 2x minus 1 plus 1 over x. So as x goes to infinity, if this term here we take it in the left side, we get that the limit here equals the limit of 1 over x, which is 0. So the curve of f admits an oblique asymptote with equation y equals 2x minus 1, which is again this term here, the equation of the oblique asymptote. Here is an illustration of this example. So I plot the curve of the function f in red here. This is the curve of the function f. And we plot also the oblique asymptote of equation y equals 2 of x minus 1. You see that the difference between f and its asymptote when x goes to infinity becomes smaller and smaller, and indeed it goes to 0. So this is an illustration of the notion of oblique asymptote, and you see that the straight line here in green is an oblique line. Thank you for your attention. This ends this lesson. Hope that it was clear and useful for you. Have a nice day. See you later in the next lesson. Goodbye.